hour. We'll try to start right at 8 in the future, but it's always a bit rough the first week. My name is Sarah. If you didn't have me for your TA last semester, or if you weren't taking the course last semester, I'm going to give a little overview and like introduction, and then go through some logistics and ground rules. We're going to have quizzes, like attendance quizzes every week for like for the sake of your grade, and the code will always be in the bottom, let me move my mouse there, the bottom right corner of the slides. We will also have pre and post lab feedback over Zoom, just so I can try to match where you guys are at as far as speed and complexity of the topic. Okay. So the code is always in the bottom right corner. I don't know, can you see my mouse here? It's like 4285 down here. Let me laser pointer. Better? Oh, you don't see, wait, you don't see the slides? Oh no, that's not good. Let me, what do you see now? Wait, oh, I know what I did wrong. Let me stop my sharing and actually share my whole screen. Okay, is this better? I don't know which side you guys can see. Okay, do you see the presenter view or the like nice presenter? Great. Let me swap displays. Is it still presenter view? Great. Okay. Yay. Okay. So yeah, I normally, like, if you have not been in my section before, or like have not been in the course before, normally we do this all on like an iPad or like a tablet, but because we're doing programming this week, we're on my computer, and so I'm very not used to it. Yeah, this is the rundown that I just gave without the slides being present. And then I want to give a little introduction. My name is Sarah. I was asked to put my photo on the slides, I guess, for posterity, but I swear I'm not just like putting it for my own ego. And I'm originally from Houston, Texas, which is the star on the map. I went to undergrad at UT Austin, which is little symbol right here in the middle of the state. And I studied electrical engineering there. And I graduated, I guess, oh my gosh, 2.5 years ago now. I had a integrated bachelor's and master's program and got both degrees in 4 years, and it was very efficient. And now I'm doing a PhD at MIT, which is in Cambridge, Massachusetts, for those that don't know. And I work specifically on quantum simulation, which I guess that can mean a lot of things, but I work specifically on designing and performing experiments on quantum hardware that emulates the behavior of different systems, like interesting chemical or biological systems can be, I guess you can make a quantum computer that just in its natural state kind of evolves like those systems evolve. And that's what I focus on. And I work with NASA some on that, and specifically Quail, which is in the Bay Area. It's like a quantum AI laboratory, and they're great. And they're very like helpful with like kind of doing more theory work. So they're wonderful. And I guess to get to know you guys a bit, I wanted to ask your favorite seasonal food, whether it's like holiday related for those that celebrate holidays around this time of year, or just like wintry seasonal things. And I'll try to go through them after I get through the logistics and ground rules and go to the attendance slide. But okay, thank you all so much for putting that in. And me forward. So as far as this week goes, sorry if you see me like looking to the side, I have my monitor like here. I'm gonna try to make it less terrible. This week's homework is a technical assessment, which is trying to gauge where you are as far as background knowledge, especially if you're starting a semester into the course. And we will be using Canvas for all of the course information and materials, except for I guess questions are all through Piazza. The only time you should be using Canvas for questions is, I guess actually never. You should not be using Canvas for questions. I don't really check it. I do check Piazza, and all the TAs check Piazza regularly. Some TAs do check Canvas, but if you want to send something directly to a TA or to the coding school, you should email this email student@qubitbyqubit.org, because we, like as TAs, we don't actually have the ability to deal with a lot of like more grading or like if you can't make a certain lab, if you have some logistics difficulty, like I don't have the authority to deal with any of that. Okay, great. So also today we'll be using Replit, which if you took last semester of the course, we did use it, so you should have it all installed. But if you do not have it, you just go to this, like I guess there's not a link that you guys can easily click, but it's just repl.it. It's a really convenient, I guess, like development environment that doesn't make it, or makes it so you don't have to download any of the software yourself to run Python, or actually you can do any number of programming languages on it. I'm sure not quite all of them, but an awful lot of them. And it's a really great resource. So it's also convenient if you're concerned, if you're not used to programming and you're concerned about breaking something on your computer. You cannot break your computer if you are programming on this. It is like physically impossible because it is all running like on their servers, and they will not let you break their servers. So it's a nice addition, I guess. And then also as ground rules for the purposes of lab, we want to make sure that everyone feels included. So please, if you feel like you are very like outgoing and able to ask a lot of questions, or especially if you ask a lot of advanced questions, I'm sorry if I don't always get to more advanced questions, because if they'd be too much of a tangent, I don't really want to go into that in lab, but you can always ask on Piazza and get a more in-depth, more technical explanation for something if you are interested in that. And also please do not spam the chat with the same question or the same message. And don't put answers in the chat unless you've been asked to, because we do want to kind of go through step by step so that no one feels like they're falling behind, because there is a very large range of experience in this class. We have people from beginning of high school to people that are partway through their undergraduate degree or have an undergraduate degree or even a master's degree and are in the workforce. So there really is a wide range of backgrounds. And I would also just like to remind everyone that like because of that, like you should never feel like you are not qualified or you don't have the, or you're behind in the course, because people are coming from so many different stages of life, and even having seen something unrelated but similar before is really helpful. So yeah, okay. Let me put this over here while I'm at it. Okay, I think this section might just be high school, but I'm not 100%. Some of the sections, most of the sections I teach have a bit of everyone in it. Okay, cool. And so here is the attendance quiz, and while we go through that, I will go through all of your fun food things. And also, if you guys have cameras available to you, we wanted to get a little group photo for the course. So if you wouldn't mind turning on your camera, I don't think we're going to post anywhere, but if you're not comfortable, feel free to turn off your camera so that you will not be in the photo. And I will go and do that. Thank you, everyone. Okay, and so I will, while everyone gets that set up, I'm going to go through the chat. So Noah said pumpkin pie. Jade, peppermint bark. Oh, I love mint and chocolate are so good together, and so many people hate it, and I don't understand them. But Drew said apple pie. Apple pie is really good. Flan from Carmen. Nice. Michael, I appreciate that every season is chip season. That is true. You can have chips any time of year. I definitely noticed that back in spring when it turned to summer, I was really into baking bread at the beginning of the pandemic, since everyone was. But unfortunately, we don't have AC, and so it was just infeasible to have the oven on in the summer, and so I just stopped making bread. Yeah, okay. Thank you everyone for turning on your cameras. I'm gonna try to get as big of a photo as I can with as many people as I can. Yeah, it's so nice seeing all of you, because I haven't seen most faces. Like some of you always have your camera, like thank you, Clark. You're always like, I'm always like, ah, someone's paying attention, someone's alive. Okay, I'm gonna just take a screenshot of this. So I'll count down so you can smile if you want to. But 3, 2, 1. Great, thank you everyone. And I'll try to get a couple more. I think I just got one screen worth, so I will do one more. Okay, 3, 2, 1. Great, thank you everyone. So fun. If you want to turn off your camera, feel free. But I also like seeing people so that I don't feel like I'm all alone. So I'm always happy to see all of you. Okay, next. So we have the attendance quiz and the passcode. So we've gone through that. If you ever don't remember it, we'll be going back and forth the slides this time, so you'll be able to find it in the bottom corner. And now I want to ask if Katie wouldn't mind starting the pre-lab Zoom feedback. Lisa, if you guys can just say how well you understood this lecture this week. I know a lot of people have covered Python before, so maybe it's not the most, like, I don't know, helpful to go through things super in depth, but also I know NumPy specifically, which is what this lab is going to be on this week. There's a lot of math that you don't typically, or you don't do super commonly in high school or for a lot of applications that we'll be doing today. That's I guess not specific to quantum, but is very commonly used in quantum and isn't necessarily as commonly used in other fields. So I'm gonna try to move my mouse like a tiny bit more. Oh, that's as far as it goes. Okay. I feel bad just like looking off to the side, but I just also can't do much. Okay. So I'm getting mostly 4s and a few 5s as far as this week's material. So I will try to keep that in mind. Thank you everyone who's filled it out. And now, oh, I've gone too far. This lab is primarily trying to give justification for why we're learning Python and how Python specifically fits into a quantum computer, or how it fits into doing like quantum computing research, or I guess programming a quantum computer generally. We're specifically going to focus on NumPy, as I said, just giving a brief introduction of how a Python library is used, how you can import it, and then creating and modifying vectors and matrices with it and performing math on those vectors and matrices. And then we have optional content as usual at the bottom, noted in blue, which I will be going through, but the slides will also be posted onto Canvas. So I often go overtime with the optional content, so there's no expectation to stay late. But yeah, also if you have covered Python before, then this will probably be your review. But I know there's no expectation that you know Python. So if you have never used Python before, we're very excited to have you, and hopefully this will be helpful towards getting you started. Cool. So to kind of go back to one thing that we covered a lot last semester, where we want to try to program a quantum computer. And as someone who just wants to control this computer, and you see this mess of wires, it's a bit intimidating. Like, how do you actually control it? Well, as like what I do in lab is kind of the more nitty-gritty like electromagnetic control of this, but what you guys will be doing is just writing code that will be converted into these electrical and magnetic signals automatically without you having to do anything. And the way we're going to do this is using an interpreter for specifically Python code, which is a little symbol there. And these electrical and magnetic signals are what we use to actually perform quantum gates. You can apply pulses of a frequency that corresponds to the qubit and perform like rotations on the qubit in that way. So there's certain amounts of time you'd want to apply this pulse, but all of that is controlled by the compiler or the interpreter. I mean, in the case of Python, it's an interpreted language and a compiled language, but often it will compile things to a lower level programming language that you don't have to know or understand. And then these electrical signals we can get back. So that's how we read out our qubit state, but you'll just receive all of these as like code when once we get to the point of running things on a quantum computer. You'll be able to see things coming in and out based off of what you've programmed into it. So yeah, that's why we use Python specifically, is that the quantum programming languages that are most commonly used, like IBM's Qiskit, is written for Python. And so it's the most convenient to know Python code. It's also a pretty simple, high-level programming language compared to many. And so it's a good idea in general. Okay, so now I want to go through a couple, like kind of a brief overview of Python. So again, it's just a general purpose programming language. Like it's not anything special, but the really unique part is that there's additional libraries that you can use for certain types of problems. So today we're going to discuss NumPy. Oh, I have something in the way of this. We're going to discuss NumPy, which is used for numerics and mathematics with Python. There's also SciPy, which is a like scientific computing, or I guess like a scientific like library that I mostly use it for constants, but there are different like functions that are commonly used in different fields available there. And there's also Matplotlib, which you guys will be seeing, I'm sure, very soon, because it's used for, like, it's the most standard library to use for plotting and creating figures and graphs in Python. And if these words aren't super clear to you, I guess, like as a concept of what a library is, we have an analogy with if Python was a phone. You could have each of these libraries as an application on it. So they're all things that you can add to your Python, I want to say distribution, but it's not totally accurate. I guess like if you have a Python project or a Python file that you're working on, you can import each of these, which is the same thing as downloading an app, and then you have access to all of these different functionalities that are already built in, so you don't have to program them yourself. So they're very convenient to have. Again, we're going to be working with NumPy today. And again, this is just kind of what I said earlier with why we might want to use Python specifically. There are other quantum programming languages that exist, or like, I guess it's not really totally fair to call it a quantum programming language, but a quantum language that you can, or use a language, or not a language, a library you can use for designing quantum circuits or performing quantum algorithms. There's Qiskit, which is what we're going to be covering, and this is developed by IBM. There's also Cirq, which Google developed, and you can kind of tell it looks kind of like all the Google apps, a slightly different color scheme, but pretty similar. Google and IBM generally are the two biggest players in quantum right now. There are other companies like Honeywell that have pretty competitive quantum computers, but Google and IBM are the two biggest, especially as far as superconducting quantum computing goes. So they're really the people that you're going to keep hearing about if you, like, especially in the news, but also in this course, whenever we reference something that they're working on, it's probably going to be one of these two. Okay. And now I want to give a little more detail with NumPy. So NumPy, again, NumPy is used for numerics with Python. If we want to encode a certain quantum state or a certain quantum operation, we can, as we discussed last semester, we can easily do that with a vector for our qubit or a matrix for our gate, and we can multiply the two to get our output state. And performing this kind of operation in NumPy is really simple. because it is built for these kinds of matrix operations. So the math we learned last semester that we learned how to do by hand can also be implemented in code. The reason why you want to learn to do it by hand first is so that you understand it a little bit better. It's really easy to kind of black box what you're doing. And I guess black box is a really common engineering term. I don't know if we've covered it, but it's the idea that you could put everything inside a like impermeable black box. You don't know what's doing inside, but you just have like wires going in and wires coming out, and you know that it does what you want, but you don't know why or how. So that's kind of how a lot of programming can go. If you have everything stored in different variables and you multiply two of them together and you get an answer that you don't expect, it's good to be able to verify by hand like where it may have gone wrong. So this background knowledge for the sake of debugging, and also just it's good to know in general how all of this works for your own intuition as you work through these things. Especially if you're trying to design something, you don't always want to do all the math for more simple things, because there is going to be more complicated math that you'll have to do. Okay. Okay. So now I'm going to try to go back and forth between the slides and code. So I've left the presenter mode, but I'm going to give a brief overview of what we're doing, and then I'm going to show you how to do it in Replit. So if you have your Replit, like no reason to open it quite now, but you can if you want. So the first step for using NumPy or any library is we need to add libraries to our Python, or to our, I guess, like Python file. The way that you do that is by saying import. Does anyone know why you might want to have, or why you need to import it rather than just using it off the bat? Does anyone have any idea why you might want to do that? Ooh. Thank you, Angel. It's not integrated. That's very true. Elon, because you don't waste memory. That is kind of the biggest thing when you start working with a lot of libraries. Eric, it's not built in, and the reason for that is typically memory. You Russell and Adam and Dhruv. Carmen, there's also, so Carmen, that's a good point. So the computer has an idea of what to refer to. So that's a very good point. In addition to not wanting to have all of these different libraries imported all the time when you're not using them, maybe you don't want to import all the functions, or you don't want to have like so many functions juggling around, especially if you import things inside your namespace. So if you can import, like you can do this thing, let me see if I can type it out, where you do like from NumPy import star. And what this means is you import the functions without, so you can use them without saying NumPy dot whatever. You can just use the function with its name within the library. And so you can choose when you're importing how you want to refer to all these functions and all these objects. And if you import all of them all the time, you're going to have conflicts probably in your named functions. So there's a very good reason, there's many very good reasons to use imports like this. Yeah, thank you everyone. Okay, so now I'm on Replit. Can you guys see this? Yes, no, maybe. Cool. Okay, so we're just going to do that. And if anyone wants to follow along, I'm just going to do import NumPy as NP. And it always tries to correct to NumPy. I don't want it to. Okay, great. So now I've imported NumPy. You can run it and it's not going to do anything because we haven't actually done anything yet. There are other ways, like this NP here is just the name we've chosen to use for NumPy. So it's a little bit quicker to type. But you could just import NumPy and follow along with the rest of the lab, but writing like numpy dot whatever function we're going to use from it. But I'm going to keep consistent with how we're doing it in this lab. Okay, so now let's go back to the slides. Okay, great. So now we want to define a array in NumPy, and the way that we're going to do that, or I guess to give you an overview of like what array we might want to do, we have this we've written out. It's just a 4-element row vector with 3 values being real and 1 value being imaginary. And that's going to be something that's a little bit not tricky, but unique, or like you're going to have to think a bit whenever you want to type this in. This is the Python code version of what we want to create. So we're using the library NumPy, and we're using this dot, which is taking like an element of this class. And we're from the NumPy library, we're taking the array function. And you have to use parentheses to access it because it is a function, not a, I guess, like built-in value that it predefines for you when it initializes something. So we will have some, I guess, objects of the like NumPy library that are not functions. And so I just want to note that so it's not as confusing. But yeah, so all we do is we have this 4-element list. These square brackets here do mean it's a list. And you see the 1, the 4, the 6, and then the 7i is actually written 7j here. And the reason it's written 7j is that is the engineering convention for the imaginary number. The I is what's used for physics. The reason why, like you will see a lot of both. The reason why we've used I thus far is because I guess most quantum information is written for and by physicists, but most computer science is written for and by engineers. So there's always going to be the J instead of the I. Does anyone actually know? I'm sure Clark knows. Clark seems to know a lot of things. Does anyone know why we use J instead of I for engineering convention? Not to call anyone out, but. Ooh, I've gotten some good ideas from Adam and Angela. It's usually used for iteration. That is true. That could be a confusing aspect. But Jonah, you have it right on. I is used for current for electrical engineers. So whenever you have a circuit, like your light, I don't know if you can quite see it. Whenever you have a light bulb, there's a current going through it to power it. And that current is always represented by I. Oh, wow, you didn't know. I'm happy to have taught something. This is exciting. Yeah, so that's why we use J instead. And so it's a good point. Isn't capital I normally used for electrical current? Yes, if it is like a static, like constant current, but if it's a variable, normally we use a lowercase I. So it rapidly does become quite confusing. There's a similar, I guess not similar issue, but I guess a notational issue with like in optics where you have like reflectivity and like all these like different variables that are all R, and it's very confusing. And it's quite difficult to keep track of. So just avoiding having the same letter is really helpful because you have like reflectivity and like reflectance, like a bunch of different like versions of the same thing that are all slightly different, and they're all R, and it's all just so confusing for no reason. But that's why you normally graduate to Greek letters pretty quickly because you run out of like Latin letters to use. Yeah, we don't use Greek letters. Just for anyone who's been like, why do we have all these horrible symbols that I'm not used to? It's because we ran out of other letters. It's not to make it look more confusing, I swear. Yeah, so now if you guys want to follow along and do this in your replit, I will do it in mine. We just want to create our array. We're gonna do numpy.array with our function. We're gonna make a list. I think this is like 1, 6, 3. 7i, maybe? I don't actually have it open. Or 7j, oh my gosh, I said it wrong. 146. Okay, I'm not quite right. Okay, I'm really struggling today for some reason. But this should be 6, this should be 4. And so we've created this now, and we can print it just by enclosing it in this print statement. And you can see it written out. Because we have an imaginary part here, all these are written as complex numbers. So you can see we have our 1 plus 0j, our 4 plus 0j, our 6 plus 0j, and our 0 plus 7j. So this is if you had an entirely real array, you wouldn't get these imaginary parts explicitly noted. Yeah, this is also, we are not doing multiplication in this case. We are accessing an element of the NumPy library, or like the NumPy class. But I hope that we don't have any multiplication with the dot, because that'd be very confusing. But hopefully we do not. Okay, so now we want to try to find a specific array index for an element of the array. So in this case, the example we've given here, I guess I'll give you guys the explanation, then I'm going to ask you if you know what element it's going to print. So to take the element of an array, you want to use these square brackets. And I'd like to note that the array indices all begin at 0. So we say this is indexed from 0. So instead of counting 1, 2, 3, you count 0, 1, 2, 3. So if we go through this list, it's 0, 1, 2, 3. Does anyone know what this A and then in square brackets 2 is going to print then? Ooh, you guys are good. Thank you, Alan and Calvert and Tomas, for your 6 plus 0j. Very nice. I'm very impressed. But all of you that did not include the imaginary part, like Aaron and Patrick and Xavier, you're all also correct. The computer doesn't know whether or not we care about the imaginary part, but I just found it very funny that you guys like got it right. Like, it's definitely going to show up, and you're totally correct that we will end up with the imaginary part printed out. But now we can actually print this if you want to see what this gives. If you ever aren't sure, you can also just run it in your replit and you'll see the answer. And you can see it gave 6 plus 0j, exactly as you guys said. Yeah, great. So that's how you print an array, or that's how you access a particular index of the array. And then of course you can just print out anything, and you'd like to print it out if you want to see it, because otherwise it will just store it, and Python will know what the answer is, but you will not. Okay, so now we're going to use a couple more NumPy functions. So we want to now use the NumPy shape function, which will tell you the dimensions of the array. So if we've defined an array like we have before, and we run this shape function, or actually it's not a shape function, it's a shape, like, I think it just stores a tuple, which is a type of Python object. It's a tuple is something that's like 0, 1, 2. It's not a list. A list is in the square brackets, and tuples have like slightly different like default behaviors. But I believe that this just is a tuple that is automatically initialized when you run numpy.array. It initializes a tuple called shape that stores the dimensions of the array. So I will go and show you running shape on our array, and you can see it's said that it's 4, nothing. So it's a length of 4, but because this is really like we haven't defined this as a matrix. It kind of goes to like it has like a default behavior and I believe it is that it treats it as a column vector, but we can explicitly note what dimensions we want. Instead, I used the wrong copy key. We can instead initialize it explicitly as a matrix by including an extra set of square brackets around it. And this like tells it in 2D that it is just this one column of elements. Oh, I should actually print the array, shouldn't I? Oop. Oh. Sorry, I've been working in Windows all day, so I keep hitting the wrong key when I try to copy things. But we can instead, if we instead initialize it like this, it then explicitly notes that it is a one column, 4 row vector rather than just having like the length of the element. So that's something that we will see this in the future, just to make it clear for you guys. Okay, so now our practice problem is to define a new array, B, and then print the second element of B and find the size of it in the same way that we've done for A. So I guess I'm sure you guys can just look at the array and tell me what the second element is. But I'll give you a second to type this in to your Replit, and then I will go and do the same. But if anyone would like to post in the chat now, I guess if you've done it, send what the second element of B that printed out was and what the size of B is. And I'll know if you didn't do it if you give me the wrong answer, because then you clearly didn't type it in. I guess this is actually quite confusing. Whether we want, what is the second element? Is the second element, actually this is the 0th element, this is the first element, and this is the second element, but there are different conventions. So some people will, I'm gonna say in parentheses, we want the 2 element, or to make clear. Yeah, so it is confusing. I typically just default to the first element is the 0th element, because otherwise I get confused. But if you can handle 2 different numbers in your head at once, then maybe you don't have to refer to it that way. But unfortunately, I cannot. Okay, great. Thank you to Joshua and Drew and Amy and Tomas and Audrey and Xavier and Demir. Yes, the second element is -4, and we can see that if we define this array. I've already forgotten what the values were. 0.5, 0.6, and -4. Oop. And then we can take the second element, print it, and I'm going to just comment out all of this so it's not bogging us down. Oop, there we are. And we got -4, and this assumed it was, or again, teaching moment, because I didn't think of this. Since these 2 elements are floating point, it has stored the entire array as floating point, so it has printed it out with the 0.0 on the end. If these were all integers, it would not store it as a floating point array, it would store it as a integer array. And the reason for this, the reason why you get this extra information is it actually takes more space to store a floating point value versus an integer value. So we'll always default to the simplest storage mechanism it can use. You can cast whatever thing you've made to a different data type, but by default, it will always use the simplest one, or the least memory intensive one. Oh, and also, yeah, if you guys want to know how all these hash symbols are commenting it out. If you want to do it for like a highlighted region, you do Control/ or Command/, depending on whether you're on a Mac or a PC. So I'm pressing Control and then /, it uncomments it. Press it again, it comments it. So that's a really helpful keyboard shortcut for Replit. It's the same shortcut as is used in Visual Studio Code and I believe in Jupyter Notebooks. So it's convenient to know. Great, so I'm going a bit slow, but we don't have too much more to do, honestly. Okay, so now we've found the size of an array, and now I want to do some math. So what I want you guys to do is now try to do some math these arrays. So you want to create 2 arrays. A and B that are the same as our I guess, state vectors that we typically use, our 0 state and our 1 state. And then we want to create our additional arrays C and D that are equal to these values. And you can do that just with the arrays themselves. You don't have to do any like math with the specific elements. And there's a little hint in the corner that you want to use the numpy square root function to do this. And I'll give you guys a second to do it, and then I'll run through it. But while you guys are thinking or typing, does anyone know, or does anyone remember what the C state and the D state are? Because you've seen them many times before. Nice, thank you, Eric and Angela and Xavier and Mason and Noah. Yeah, the C state is our plus state and the D state is our minus state, exactly as we've seen many times last semester. Thank you, Avanaba and Dhruv, Tomas and Surya, Elon. Yeah, they're all, it's all the same thing. It's going to keep coming back. So you never have to remember anything, or yes, you do have to remember things. Obviously you remembered this, but you don't have to remember new things that often. Most things are the same thing, but just a little bit more complicated. Okay, so now I'm going to go to Replit and create these arrays. So what we want to do, comment this out too. We're going to create our array that is our 0 state and our array that is our 1 state. I guess this is the right way to do it. Okay. And then we want to create our C state, which is equal to 1 over the square root function of 2 times A plus B. And similarly, we want to create our D state, which is the minus of these. And then we can print out all of these states that we've created. I'm just going to do this like inefficiently, but this is D, C, and B. Hopefully I did this right. Nice. Okay. So yeah, we have our 0 state there. These are all written, I guess, as not clearly as like column vector form. If you want them to be in column vector form, you can again just put this extra set of parentheses or extra set of square brackets around them, and then it will write them. Or this doesn't write them as a column vector still. Oh wait, I think this is actually a row vector, and we need to take the transpose to make it a column vector. But we're going to cover that in a second. I'm always very confused by Python conventions, so I promise I know what I'm doing, but I normally have to try it both ways, and then eventually one of them will be correct, the other will be wrong. I'm not good at remembering things that are like a 1 or a 0. If there's more than 2 options, I'm better at it somehow. Okay, so that's how you create those states. And now we want to create a transpose for these states. So we're going to do, we're going to take a transpose of what we've already made, and you'll see that it prints as a column vector instead of a row vector. So if you've created a column vector, then its transpose, to remind everyone, is just moving the elements from the first row becomes the first column, the second row becomes the second column, etc. And if you have a row vector, the first column becomes the first row, second column becomes the second row, all the way through. So we can change these all into column vectors by taking the transpose, which this dot again is just taking, whenever we create a array using the numpy array function, it initializes a bunch of things that are built in to numpy. And so we've already defined this transposed version of the array. And so we're not even calling a function, we're just calling the transpose of it. And you can see that it now gives us column vectors for everything. So we have our 1, 0, our 0, 1, our, like this is square root 2, but like our square root 2, and our square root 2, negative square root 2. Exactly as you'd expect it to do. So it's just made this whole transposition process much more simple, especially if you want to do large vectors. We don't have to do that manually. We can just do it in code here. Okay, so now we're going to do the second part. I was going to ask a question, but you can see it in the little preview because I'm not in presenter mode. But the second part of our very common complex conjugate operation that we do in quantum so much is taking the conjugate of these arrays. And to remind everyone, the complex conjugate, you can, I guess, write it out with a bar on top of your complex number, or you can equivalently write it with a asterisk or a star in the upper right. And all it does is it takes, I guess, takes all of the imaginary numbers in the system and multiplies them by -1. So our plus I is now minus I, and if we had a minus I, it would become a plus I. And so we can do this operation in NumPy using the conjugate function, which is conj, or like C-O-N-J. It's written here. And it is a function, so you need the parentheses for it to work. And I'll give you guys a second to do this little practice at the bottom, where you want to create an array that is 1 over root 2, 1j, and take its conjugate transpose. And as soon as you've done that, you can post to the group. I know you can also do it by hand. I know it's only two vectors, but if you do it in Python, you don't have to type it out. Or I guess you still kind of have to type it out. But you don't have to type out the minus sign. So you save one keystroke. So. Cool. You guys, second. I know we're running a little short on time. We don't actually have too much more content to cover though, so I don't think we'll go too far over. Thank you, Drew, for noting you are done. I appreciate that people have completed things. Yeah, you can also, like, if you want, you can send your result of your conjugate transpose print statement if you want, but I'm not too bothered either way. I know it's quite straightforward because it is a pretty small operation. I'll give you guys one more second and then I will go through and do it as well. So I'm gonna comment all these lines out again because I don't want them. And we're going to create this array. It's 1 over np square root 2 times np dot array 1j. Oh, didn't put square brackets around them. And again, to make it explicit that this is a matrix, you guys do want to make sure to put the 2 sets of square brackets on each side. Thank you, Tomas, for your results. Yeah, so we want to make sure to do this to so that we know that it is a 2-dimensional matrix. Even if it's a vector, it's just more clear. And then we want to, so what did I tell you to do? Do the conjugate transpose for this. So we want to print a dot conjugate dot t, or I guess just make sure to put it in parentheses so it doesn't break on me. And there we are. So you can see, I mean, it's a bit ugly, unfortunately, the way it's printed out, but it's our square root 2 minus 0 j, and then our 0 real part and minus square root 2j. You can see we put in the plus square root 2j, so we've taken the complex conjugate of the array we put in. And it's really simple. We just need to do these 2 steps. They're done. You might not need to put the parentheses around this, but sometimes things break if you don't. I'll try it though, just for my own education. Will it still run? Yes, okay. Python's not that picky about parentheses. But I think this is also kind of hideous looking. because you are still taking the like element of the A matrix. You're not taking an element of this conjugate function, but it looks kind of like you are. So just to be clear, it might be easier to just put parentheses around it like I did, so you know that it is the result of this operation that you're taking the transpose of. But it is really just a matter of taste. Okay, so are there any questions about the content we've covered so far? We are near the end, but also we have a couple more slides that are important. Sorry, Alon mentioned that if you do the transpose and then the conjugate, rather than the conjugate then the transpose, it looks less hideous. And that is definitely true. I do like that better. But we call it a conjugate transpose, not a transpose conjugate. So I actually don't know what order of operations Python, I don't know if they do it left to right or not. So it's possible I did a transpose conjugate as I did it. Who knows? Okay, sounds like everyone's doing pretty good. I'm gonna try to get through the rest right before we hit 9, and then we'll go into the extra bits. Carmen, you need parentheses around your array function. You're missing a parentheses around your array. Yeah, all good. Oh, yeah, conjugate transpose is the exact same as transpose conjugate. It is a like commuting operation, but we just call it a conjugate transpose, so I prefer to do it in that order. Yeah, okay, so now we're going to define a matrix with this exact same way we did previously, but now instead of just having one list, I guess, then we'll have 2 lists separated by a comma within another set of these square brackets. So that, like I said, a 2-dimensional array is always defined with 2 layers of square brackets, but you can have multiple rows or columns, or multiple rows within it. So what we want to do is define this Z matrix, which you guys will remember from last semester as a Z gate, and then print the 1,1 element of Z. And again, that like you can just type it in. You don't have to think about it too hard. And you should get the right answer, regardless of whether you're confused about whether it's the 0th or the first element. So I'll give you guys a second to do that. And we're gonna go like slightly over, but not terribly over. Okay. Okay. Nice. Thank you, Avanaba and Dennis and Bruno. Got a -1. Love that. That's exactly what I expect. And I can show you exactly how you should get that by defining Z is equal to the NumPy array 1, 0, 0, 0, -1, and we can print Z 1,1. Oh wait, I should have done this in square brackets. Oh no. Oh wait, did I? Oh, that's where I went wrong. Sorry for trying to rush. Great, we've gotten our -1. Yusnahil and Woon. Yeah, that's exactly what you expect to get. So we've just defined our first matrix that I guess we've technically everything is a matrix. A vector is just a 1-dimensional matrix or a 1 by n dimensional matrix, but we've defined one now. And now we can do multiplication with arrays. And the way we're going to do multiplication is using the at symbol. So if we want to multiply our matrix A and our matrix B, we can do A at B. And for our example for it, we're going to do a little problem. I'm sorry for going quick in this last bit. We want to take a qubit state, which will take to be the 1 state, 0, 1. And we want to apply a Z gate and then an H gate. And we want to find the state of the qubit at the end. And this is the last bit. So I hope that if you guys have time to stick around just for to finish this off. But if if you've been following along, all you need to do is define another array that is the H gate, and define a, I guess, a third array technically, or you can think of it as a vector if you prefer, to describe the state vector. And then you should just perform this operation and you should get the results out. And I eagerly await your results in the chat. If you are a bit confused, oh, thank you, Noah. Yeah, I think that's correct. If we start out in the, I also hope, I will need to run it and make sure, because it's all variations on a theme. It all looks very similar. We want to define our psi, we want to define our z, we want to define our h. And so I'm going to write them out while you guys hopefully follow along, and I hope that some of you get the result before I do. So we've defined our z gate already. We now want to define our h gate as 1 over np square root 2 times np dot array. Is it 1, 1? Oh, I forgot the initial bracket. Or is it -1, 1? I always forget. Yeah, 1, 1, -1, -1. Oh my gosh. -1. And then we want to define our psi, which is array 0, 1. Okay, so I haven't seen any results yet other than Noah's, which I hope is correct. Yeah, and you never have to multiply anything ever again by hand. You just can do it in Python and then copy and paste it wherever you desire. Oh, nice, Tomas. You've also gotten the same thing. It's good that you have, I've gotten the same thing. I assume that you guys have it correct. Okay, this should be a vector, should it not? Okay, so what we want is we want to multiply the psi by the z gate. So I'm going to just do an intermediate step just to make sure we do it in the right order. It should be right to left. Woon and Alan and Devon, let me know which way it is. Elon, yeah. So what we want to do is I'll do an intermediate step. So I'll just say like A is equal to psi z, and then out is equal to h a, and then we can print our output. Hey, I got the same thing as everyone else did, so I think everyone's correct. And we can also print this as a column vector if we prefer to like see it as we normally do our states. Or, oh, maybe not. Let me, like this. Eh? Oh, wait, I did not define this as a vector. That's where I went wrong. Oop, there we go. Never mind. Okay, maybe just don't define this as a vector or it gets confused clearly. I don't know why that's from. That is a Python convention I'm not used to. But do as I say, not as I do. I always forget the Python conventions for arrays versus vectors. And then I always get them backwards, and then all my math is wrong, and it's very sad. But yeah, that's all you need to do to get that result. And I just want to get some key takeaways, and I have some optional content if you guys want to stick around, but there's no obligation to stick around. I hope you had a wonderful first lab, and we will be back next week with more quantum. Yeah, so the key takeaways this week's lab is that Python is good to learn. The libraries you can use to extend the functionality of Python, like NumPy and SciPy and Qiskit, are very helpful for specifically doing quantum computing work. And we can do all these qubit rotations and quantum circuits entirely with Python without having to do anything by hand. So I will, Katie, if you wouldn't mind opening up the post-lab Zoom feedback, I'll just quickly go through a couple of extra bits about how to use arrays in Python. So you can, if you want to define a very large array of numbers, it can be quite inconvenient to do it by hand. Like you don't want to write out 1 or 0 or whatever a bunch of times. The ways you can do this for this A vector example, you can write np.zeros, the size you want. So it's written out, I guess, here. And I can show you exactly how that works in Replit. We say A is equal to np zeros, 1, 4. You can see we've gotten an array of 4 zeros. We can make it much bigger though. We could make 100 zeros and it runs almost as quickly and I don't have to do anything. And it's very convenient. And it would take me forever to type that out so far. So it's really nice having these kinds of functions. There's similarly one to create ones and to create matrices. So this example, C is equal to np.full. Full just means that it's fully populated with whatever number you put in. You pass in a tuple of the size of the matrix you want and whatever value you want. So I'll actually mix it up a little bit and say C np.full of 2 pi. And we can print that. Oh, why did I make it so big? That's gonna take forever. Oh, I made it. I don't think that's actually 100 by 100. Oh no, I did it 1 by 100. What if we did like 10 by 10? That'd be pretty fun. This bit is only useful if the elements are the same. You are correct. However, thank you, Surya, for your little like hint. What if we want different elements? Well, you can define regularly spaced arrays very easily using the two functions numpy.arange or numpy.linspace. And they both work in slightly different ways. Arange, you define the starting point, the stopping point, and then the step size. And you can see it does terminate at 98, not at 100, because the way that generally definitions work in Python is you go up to like n-1. So in this case, because the step size is 2, n-1 becomes 98 instead of 100. And that's just a convention it's very convenient for iterating through something like many times. But that's, if you're confused by it, like that's why it is like that. NumPy.linspace works slightly differently, where you give your starting point, your stopping point, and the number of points you want in between. So it will put 50 points in between 3 and 4.5. So there'll be some decimal value in between these two. And I can show you exactly how this works. I'm just going to define it as C. Let's do linspace 3, 45, 50. And you can see it's given us 50 evenly spaced points between these two values. Similarly, for the arange example, let me just move that in. We could do, that's what was our starting point like? Let's do 0, 45, and do steps of 3. And you can see we've gotten every third element up the ladder to I guess n-1, so we've gone to 42 instead of 45. Yeah, that's all for the lab. Any questions about it? Dylan, why is it called linspace? I actually don't know. I think it's like a linear, it's linear something somehow, but they use the same term for MATLAB, so linearly spaced. That makes sense. Thank you, Sarah. Yeah, no, I learn new things every day, and most of them are things that I think like I should have realized, but I just did not and would never if someone did not tell me. Okay, any other questions? Thank you everyone for the great first lab. And also, if you're still around, if I've said your name wrong, please like just tell me that I've said it wrong, and like you can come on like chat and like say how to say it right. I know like I try to like get everyone's name right, and I do secretly jot down names and look them up so that I like hopefully do them right in the future, but I know I don't always quite get it. Yeah, thank you everyone. Yeah, that's it for this week's lab. See you all next week. Thank you everyone.